So thank you, Poon, and to all of the workshop organizers for giving me this opportunity to talk today. And again, I think Poon and Lee and everyone yesterday did a fantastic job of level setting, if you will. But I just wanted to go a little bit more into, using differential privacy in the context of genomics, why we have any issues, if you will, and what can we do about it. So why is genomics a stress test for privacy? I mean, this is something that Hoon talked about yesterday. One thing that we actually saw, and I don't want to go into this, but the Human Genome Project has actually been a fantastic success, in the past 30 years, since they sort of thought about it and then they looked at how to sequence and so on. So that has been a great success in terms of the amount of work that has been done. But one thing that has been very clear is that you do need a lot of large-scale collaboration to actually make this work. This was a very expensive exercise. It has gone down now. But what we find is that you have all of these studies happening in different places at sort of different sites covering different subpopulations and so on. You do need sort of large-scale collaboration to sort of make some of the big advances actually happen. Our real problem, though, from a privacy perspective, is the fact that DNA is not just data. It's not just transferable, that everything we do in the standard data context works in the genomics context in and of itself. Poon spoke about this. Genomic data is uniquely identifying. We all know that, absolutely. And it is extremely high dimensional. And that creates a huge problem because now you've basically flipped, if you will, the situation. We don't have lots of data with very well-specified space. You basically have a much more under-specified problem, if you will, domain, and that creates a huge issue. The bigger issue, and Lee talked about this as well yesterday, is that genomics data is relational, and there are inherent, a lot of relationships over there, which can create a significant problem from the privacy perspective for us as well. And then, what I mean by that in terms of vulnerable to changes is simply that we talk about synthetic data. Here, it is very interesting to sort of take into account that minor changes, again, the SNPs we've talked about, again, are very critical when we think about what kind of sort of deviations you can basically incorporate into something like this. And of course, when we use AI, that increases both our utility and sort of risk. So one of the things is this creates a very unique environment, if you will, from a privacy perspective in and of itself. So the bigger question, if you sort of stop and think even for a minute, is what are we really trying to protect? And then, of course, the question of how does it actually work? So in this context, is it just the data individual records that we are trying to protect, or is it the data sets as a whole? Is it models that we are trying to protect? The sort of data that is automatically incorporated into these models. Is it the individuals? And differential privacy does a fantastic job of protecting individuals if you correctly define what the individual is in this context. But since we are talking about DNA, if we are talking about genomics, is it really families that we need to protect, including your ancestors or what have you? Or even more so in this particular context, is it the unborn that we need to protect? Because really, it could be the future generation, which is coming right away. You don't recognize what exactly is the impact of that small privacy breach, which you think is small right now, but might actually have a huge impact sort of going ahead. So this is actually a big problem, this notion of what are we trying to protect. And I think this, in fact, is honestly the biggest problem that we have, even from a differential privacy perspective in this context, that we need to be able to sort of define not just the boundary, but also say what do we really want to do? What is it that we are trying to protect? And this is why I won't go into this. This is all of the traditional privacy work, de-identification, aggregation, access control, controlled repositories. All of this is important. All of this is insufficient. It's sort of necessary, but not sufficient to sort of protect privacy. But honestly, the same applies to traditional differential privacy as well, because, okay, it does really well when we have records that are unrelated to each other, we are looking at them uniquely. That works perfectly, but this is not going to be sufficient. This is really our bigger problem, if you will. So the one other thing, and again, I just wanted to reinforce this once more, genomics does challenge our classical privacy assumptions. And this, again, we heard this yesterday, but I want to reemphasize the point once more. We've got these issues like shared ancestry between people that you have to take into account. So even when we talk about relationships, it may not just be your immediate family or what have you. It could be something broader. There are specific traits that are actually shared, if you will. Population structure, this is complex, not just at the individual level, but at the group level as well. And there are these inherent sort of structures there as well. The long-term persistence, I can't just go and revoke my DNA, so to speak. We don't have those great options in front of us. That creates its own issues in and of itself. And as I said, the fact that one genome can affect others. There is, again, even if not necessarily causality, but sometimes even that in terms of changes in one space actually resulting in changes in other functional loci. Stuff like that. So these things really make a difference in terms of the privacy assumptions that we have. And again, I just want to reinforce, defining the problem is half or actually even more of the battle, right? If you can define the problem, define the context, then that actually makes it a lot easier. So in that sense, we have sort of three emerging views of privacy. The individual privacy, which actually differential privacy does a fantastic job of in terms of capturing and taking care of. Relational privacy, which is really important in this context. Relational privacy is something that we do need to work on, and I'll talk a little bit more about this. And then contextual privacy, which is something that came up yesterday as well. And what do we mean by this? Why does it change? Why does it matter in and of itself? So relational privacy, again, to reemphasize the point, in genomics, privacy is inherently shared. So you can't talk about your privacy to the exclusion of people around you, to people you're related, so on and so forth, because the genome reveals sort of information about me, my relatives, about populations as well. One quick thing that I wanted to talk about, this is some recent work that we have done, and I won't go into this a lot, but I did want to make this point because we are talking about synthetic data as well. So in fact, it turns out that in the raw genotype space, synthetic data may appear very safely distributed. But if you look at relationships, you can actually have these invisible we have this identity by descent, a new membership inference attack, where we are replacing this notion of is this point identical, but does it share inherited structural segments with some specific training target? And you have these invisible threads that suddenly that nice synthetic data, which looks beautifully spread out, is no longer quite as spread out. And again, I won't talk about this. This is, in fact, too much, but I am going to say that looking at those relationships makes this membership inference attack way stronger than the existing state-of-the-art membership inference attack. So the four things below are state-of-the-art attacks right now. The top two basically are two instantiations of this identity by descent attack, depending on how many related records you want to actually look at or top records you want to look at. So relationships really matter. That can make a difference in terms of the attacks that you can create as well. The other thing I wanted to quickly touch on, just to stay on time, is this notion of contextual privacy, right? So what are we trying to do and why are we trying to do it changes, of course, the kinds of privacy risks that we actually see. So Lucilla spoke yesterday about academic collaborations. Even when you're not trying to sell the data, you're trying to do just science, so to speak, you have lower risk, but there are different sort of questions whether people, doctors are willing to necessarily share and so on. And even there, you have to be very careful between the differences for clinical use versus for scientific research, right? Certain things may be okay in a specific context, but may not be if you cannot establish a very specific, need, which is urgent, so to speak. So we have different risks, whether you're trying to do a synthetic release internally versus trying to do, say, clinical use in a very limited context. And of course, public dissemination is a huge problem in and of itself. So that is not something that we have solved. But we do need to, the same genome has different risks depending on the specific context. And then that really matters, what you're trying to do with respect to it. The one other point that I wanted to make in this particular case, very, very briefly, I know the next talk is actually going to talk about sort of genomic language models as well, but this is some recent work that we did. In fact, it's going to be presented at the end of this month at the BCB conference. We were interested in looking at the foundation model thread. Basically, are genomic language models memorizing patient DNA the exact same way ChatGPT memorizes text? And the answer, unfortunately, is yes, by the way. And here, all we are doing are, in fact, planting canaries into the data, duplicating it at different levels, maybe instead of, having it uniquely versus having it 5, 10, or 20 times, and then trying to extract information about this. And in and of itself, as Peter talked about, we are not making very special canaries. These are actually very similar, randomly created things. Nothing, that would stress test things. And it turns out, though, the one thing we realized is that you do need to use different threat modalities. So we actually thought of using perplexity, again, to see the interpretability of those models. Is it assigning suspiciously low loss to those canary sequences as compared to held out data versus direct? So the perplexity check is sort of implicit, no extraction being carried out. But now you can actually try to sequence extraction. Can we prompt it with a sequence prefix and coax it into generating the exact training sequence verbatim versus, of course, traditional membership inference attack success, looking at likelihood ratio attacks. Is this able to work? And what we actually found out was basically some interesting things. I'm not going to talk about all of them. But first of all, duplication-driven memorization scaling, actually, those scaling laws transfer perfectly from text to genomic AI, which is very, very interesting in and of itself, right? The second thing is memorization is not a unitary phenomenon. What I mean by that is that certain models, and we actually looked, I would say, from DNA BERT, Hyena, all the way up to EvoLoRa, so to speak, different models perform poorly in terms of different attacks. And, from a privacy perspective, that's bad. It doesn't matter that you're doing well against attack X if you're basically sucking at attack Y in and of itself. So even if you're fine with sequence extraction, you may end up doing really poorly in terms of perplexity or others. And the worst part, this was very interesting, the parameter efficient fallacy. What I mean by that, we sort of assume that, if I have really large models and I'm not doing complete fine tuning, I'm just basically approximating, that gives me privacy. Guess what? It doesn't. So in fact, EvoLoRa, which is, again, the largest model, does perfect sort of memorization, and we are able to extract almost 100%, if you will, for particular canaries. So this is really bad news in and of itself. A couple of final things that I want to talk about. This is something that was touched on as well. I think Joe talked about this yesterday too. If we look right now in operationalizing this, we've got two words. On one side, we've got epsilon, delta, composition, things like this. And on the other side, we have, of course, in the medical context, risk, benefit, participant protection, things like that. And we really need to bridge this divide. I think that is, in fact, the most critical challenge that we currently have. How do we move these things to a spectrum that people can actually understand? So I think that I would say we have this governance gap. Lee spoke about this too. Technical guarantees are not sufficient. We need interpretable risk frameworks. And of course, you can't go to the deep end on either side. You can't completely stop things, but you can't, just keep it open in and of itself. So one thing, and this is, I think, almost the final thing I'm going to talk about, we are actually currently developing a sandbox environment as well, which is very interesting because the idea is that you can use differential privacy and other tools to create sort of synthetic data. And the idea is not to do science with this. The idea is to use this to inform the IRB on what collaborations might actually end up being useful. So think of it as informing your cost-benefit analysis for the IRB itself. And this is actually work that we have done. We have the technical work done, and in fact, we are working with partners in the IRB to see if this actually improves the time it takes, because that's our biggest problem. You have so many different people to potentially work with. Every collaboration takes months or if not years to go through. This might give you a better idea for what is actually going to be helpful. And this we are carrying out with our collaborators in Genomics. They are going to basically re-verify the work they've done. And then we want to sort of use that as an addendum to the standard IRB protocol to basically say, hey, is this really helping? And that, I think, might be the best way to sort of move towards this. And finally, I will say, we really want to separate out process governance from the execution privacy, if you will, right? So the who and the how of things that are happening, from the where is it happening and the what. And one thing, we've always been talking about differential privacy here. Hoon has done a lot of work in collaborative computation. There are many people who worked on that. I think we do need this hybrid model. You can't stay stuck to any single sort of operational environment. We have to develop solutions that work in sort of all of these environments. So to conclude, I'm just going to say three things. You have to think from a theory perspective, come up with better models, incorporate these sort of definitions of relational privacy and so on. How do we model auditing, things like that. But then we need to move to systems where you're building these secure sort of collaborative infrastructures and even these policy-aware pipelines, which are able to transfer from the natural language sort of policies that are expressed all the way to things that are actually happening. And then, of course, finally move that to governance, because at the end of the day, that is what people care about in the health systems. They don't care about theory or about systems. They just want to know how does it meet what they need to do. So risk-aware IRB tooling, even things like adaptive access control and consent evolution. So we have to tie all three things together and make these developments to actually make this work. With that, I'm done. And that was all that I had to say. So if there are questions.
One question. So the results that you were showing on the attacks, were you taking genomics data and fine-tuning the model on? How were you using that data? What object were you attacking?
Right. So we were actually looking, yes, we were fine-tuning. Basically, we were fine-tuning, if you will, using the genomics data. And then we were looking at the models afterwards and looking at what we could extract from it. Absolutely.
And you have a patient key data set.
So yes, we basically added canaries to existing public data and then used that to fine-tune the models. So that's correct. But the interesting thing was that we actually, and this is something that we are doing now, the canaries were basically unique, unique in the sense that they were randomly created. We did not exploit structure, which is something that we do want to do, which might actually make it much worse.
So I want to drill down on the identity by descent attack you mentioned.
Right.
So is that attacking the synthetic data, the MIA on the synthetic genomic data?
So no, so the idea there is, yes, it is an attack against synthetic data, if you will, and we are trying to figure out, basically instead of standard membership inference, we are basically trying to again figure out if things are related and use that to see, if you compare with respect to the original data, how far you are, if you will.
So what is the attack? Do you still have one record?
We have, actually, it is synthetic data that is created, but when you're looking at what was in the training data, we try to see how many things are related to it. So as opposed to figuring out if that one point in your training data is getting sort of recreated right over here, or was it part? We basically try to figure that out using a bunch of different. So the k equal to 5 and k equal to 10 was looking at the top 5 or the top 10.
They know the relationship.
But we are able to figure out. So actually, that's a good question, and we use the King coefficient and a bunch of others to try to say, okay, I want to see if this would be present, and I'm going to use standard sort of measures to figure out is it related and the extent to which it is related. So yeah, I can talk more about this, but basically, yeah, we are using very standard genomic distance measures, if you will, for identifying relationships and then looking at not just in a single point sense, but as a whole,
Leverage them.
Correct, exactly.